Welcome to our April 20th webinar for StatPREP. I'm Danny Kaplan from Callister College. And today is the introduction of a new initiative from StatPREP, which we're calling Little Apps. And in just a few minutes, Kate Kozak is going to introduce you to one little app so you can see the approach. And we're thinking it might be one that you'd like to use since April, towards the end of the semester, instructors are getting close to finishing up and deciding whether or not they're going to cover ANOVA, which is often a topic that this might be supposed to be on the syllabus, but gets left out due to the exigencies of teaching and mentoring students. So welcome again. This is the StatPREP website. And if you go there, statprep.org, go down a few, you'll find a post, Little Apps for Teaching Stats. And that's what we're going to be talking about today. So I'm going to show you by example one of the little apps. It's different from the one that Kate's going to show, but to help you orient you to the idea behind them and to the overall approach. So I'm putting up on the screen here a little app. It's called the 2Sample-T little app, but actually you can use it for more than that. Like almost all of the little apps, it's centered in a display of data. In this case, there's one variable, which we call the response variable, on the y-axis, and another variable, categorical, on the x-axis. That's a very common setting for any of the StatPREP apps. And they're interactive. You can change both the response and the explanatory variables. So here, for example, I'm plotting out the household income measured in as multiples of the poverty level, and whether or not someone owns or rents a home. And often it's enough just to show a pattern in data. But these apps are meant to make it simple for you not only to talk about data, but for you to illustrate both simple and more elaborate statistical concepts. For example, I'm going to turn on the group-wise means for the homeowners and the home renters. And if we're interested in talking about sampling variation, it's just a matter of pressing a button to take a new sample, so we can see how stable that kind of those means are for these variables. And one could go on, which I won't, but you could show the stability in terms of the confidence interval on the means, and show how the confidence interval changes with sample size. And then this one has an annotation for illustrating what the t-statistic is about. And each of these apps have some graphic, some data graphic and statistical annotations that you can deploy or not. They also include a tab explaining the individual app. So this is a little narrative explaining what the app display means and giving just a little bit of background without interfering in the lesson that the instructor wants to teach. There's a code book that tells you what the variables are that are being displayed. And if you change the variables, of course, you change the code book that's being shown. And then finally, if you want to move on and use actual R commands to carry out the statistical calculations, each of the apps has examples of the calculations that underlie the apps. So you could make a transition from graphical user interface to actually having a demonstration with commands or having your students use the commands. And this is the standard format for these apps with these several tabs. We're going to show you one from the original generation of these apps, which is, say, from March, which doesn't have all these tabs, but in a few weeks we'll have all of them updated to show this. So what I'd like to do is turn you over now to Kate, who's going to show you the little app for one-way ANOVA. Kate?
So hi, everyone. I want to welcome you all to the webinar. I live in Flagstaff, Arizona, and I teach at Coconut Community College. My husband just texted me that it's snowing today at our house, so I'm excited because we are worried about fire season this year. So we're excited about getting snow. I realize those of you in Minneapolis or in other parts of the country that got a lot of snow recently aren't too happy about that, but I happen to like the snow. So as Danny said, I'm going to show you about an ANOVA little app. So I'm going to go in to show you that.
While Kate's bringing that up, I didn't mention that all these little apps are available just through a web browser. They're on a server, and you can access them through the links on that page, that blog post I showed you about teaching stats with little apps.
All right, so this is, again, one of those little apps. This is about the ANOVA with one explanatory variable. I should let you know, and this kind of goes along with what Danny was just saying, I don't actually teach ANOVA in my class because it's not part of our curriculum. We don't actually get to it, but I could see how to use it in my class and use this app earlier on to actually introduce different topics. So I'd like to look at maybe changing the response variable because to me, age versus gender isn't all that interesting. Here you have gender on the horizontal axis, and you can see you have female and male as the two values of the variable. And then age is actually on the vertical axis. And so you can kind of see here that the mean, that's what this bar represents, the mean for female would be about here, and the mean for males is about here. This different information over here is kind of showing you each one of these data values. So this dot right here is right over here. This dot right here is this line right here, and so forth all the way along. So it kind of just shows you where all the data is and how spread out it could be. So that's kind of an interesting idea. I'm more interested in something different than just age versus gender, because, and I can show you a different sample. We can again show the idea of sampling and show how you can get different information from samples. And you can see how the means changed a little bit, and then the means changed a little bit. But to me, age isn't as interesting as some other variables. So let's actually, I think we'll stick with age, but I think my explanatory variable I might be interested in is work. And this is actually, this variable has different values of they're looking for a job, they're not working right now, or they are in fact working. So this is your work variable, again, it's on the horizontal. Your age, your response variable is on the vertical. So looking at this sample, we can see that the mean for looking is down here. The mean for not working is way up here, up around 62, it looks like. And the mean for working is around 45. So I would probably ask my students, why do you suppose there's such a disparity here? And I might actually introduce this early on in the semester and just kind of talk about, why do you think the looking has a much smaller mean than the not working, and why the not working is much higher than the working? So what kind of ideas could you come up with is what I would probably ask my students and what I would do. Personally, I would think that this is the people who are out of high school and college, and that's why the mean's so low. These are the people who are retired, especially these people way up here. And these are the people that kind of are in their normal life. And you can see we even have values way down here of around 22 for working, and way up here around 65 for working. So you have this large range of values that you can see.
Kate, I'd just like to add something. If this were the new format of little apps, there would be a Codebook tab, and you could see from that that these data come from the National Health and Nutrition Evaluation Survey. And the entire set of data is about 10,000 people, of whom Kate is displaying a random sample of 50.
Right. And I can again show you how those samples change. If we take a different sample from that data set, we can see how the means didn't change a great deal. They changed a little bit, but they're not changing a great deal because you kind of expect that the looking would be people who are just out of college, and you kind of expect the not working are the people that are towards retirement age. So you would expect that to happen, though you do have people down here that are not working. And since we don't know exactly how they asked the question, somebody could have said they're not working when they're really looking. So you also have that problem with data, and you could talk about that with your class, that sometimes the questions that are asked are ambiguous and how people might answer it. Then I probably would show them, what happens as we increase our sample size. So I might go to a sample of, let's say, 100 people, and I find different information. You can see there's a lot more data in here now. That's why there's a lot more of these red lines over here, because each one represents a person, but there might be 2 or 3 right here to represent these 2 or 3 right here. And you can see how that changes. You can see, though, that the means didn't seem to really change a great deal. Let's take another sample, because we do know that data is different for different samples. And you can see, hey, something looking is way up here, because somebody probably retired and then decided they wanted to have a job again. That could be an explanation you could have your students come up with. So again, I use these as ways to kind of talk about how would I use this in my class and what would I have as a discussion. A different sample will give you this information. And so you could do that, and we could even increase our sample size even more. Let's go up to 500. And then if you keep taking more and more samples and take a different sample each time, you can see in this case, the means don't seem to change a great deal. So that kind of says to me that that maybe there is a difference between these values. So that would be something I would maybe have my students talk about is, hey, there is something going on with the different, my explanatory variable looking, not working, or working, and the different ages of people. And so then we might ask.
The idea that the larger sample size gives you more stable estimates of the mean, and that's why you see the same one every time?
Right. So that's what happens is you do get kind of the same, not getting the same data, but you're getting kind of a more stable representation. And again, I would talk to my students about that too. And you can see how that changes. And then you ask your students, well, now here, this one, obviously there was a data set that had some interesting things happen, and you might ask why. And you notice there's somebody way up here in this group, they're over here in this group of somebody who's 80 who's actually looking for a job. So you might ask, why did that happen? And these would be questions. But then you want to ask your students, have you noticed when you take different samples and the sampling variability is different, what is actually happening? And does this mean that the mean age is actually different for these different groups? And so you want to look into that kind of concept next, is to kind of talk about why that is and see what happens to the variability. So if we keep just doing a bunch, you can see those are pretty much the same. And then we can talk about what happens to the variability, because that actually kind of is also involved in what we're doing. Is the means are all stable, but why is that, and what is happening to the variability of the different samples? So we can actually look at what that variability is in your samples, and the way.
I just was wondering, do you have to use age and work, or is there another set of variables?
Let's do another one. So let's maybe look at poverty.
Or pulse?
Pulse would be interesting. Let's look at pulse. So pulse, again, we have the looking, not working, and working. And you can see that pulse is on the vertical axis this time because it's the response variable. So now, looking at this, all the means seem to be about the same. And if I take another sample, they jumped around a little bit, but they're still about the same. And if I keep taking more samples, I'm going to keep noticing that these means seem to all be about the same. So what does that tell you also is something I would ask my students is, why did that happen? What's going on? And where I would try to talk about it in my classes. And I might even at this point change the sample size to say, okay, we saw not much difference when we had a large sample. What happens if we have a small sample? You can see, hey, there's a big difference sometimes. The means jump around a lot more, and then talk about why that might be the case. And talk about that samples are in fact different and what actually happens with those.
So are you saying that with the large sample, you can see that the pulse rate doesn't change? Is the same for working and non-working people? I mean, I guess everyone has a heart that has to have a certain number of beats per minute.
Right.
You can see that they're the same, but then you can see that they're different in the small sample?
Well, you can see the more variability between your samples, that you can have an unusual sample. So we take another sample here. This sample had a data value way up here. This one has a data value way up here for somebody with a pulse. And so you can see that variability happening inside the samples because you took a smaller sample, you get to see more of that unusualness. I shouldn't say unusualness, you get to see that you might catch one of the outliers, which is what is happening. You're seeing those outliers, whereas with a large sample, the outliers don't play as big of a role. So you can still see the outliers, but they don't affect the mean as much because there's all these other data values here. So you can kind of see what's going on with those. Sorry. And so then we talk about, well, what is actually a measure of that spread that we're seeing? So here we see the spread, but we don't see a lot of change in the means when we have a larger sample. And so you can talk about what is that spread. Here you can see the spread is fairly big. This is basically looking at just all the data and what the spread is of all the data. Whereas this column is looking at the spread if the model actually does explain what's happening. So if this variable really does explain the differences between these, what does that look like? And you can see that that spread, this spread is pretty constant. That spread seems to move around just a little bit more. And of course, we measure spread by standard deviation. So we can look at standard deviation, and there's actually a button right here called Show Standard Deviations. And if you click on that, you will now see those standard deviations. So there's a standard deviation for the whole data set, and here's a standard deviation between these means, if you're using the explanatory. And then you can take more samples and see what's happening with that. So you can see lots of different samples. Pulse isn't all that interesting because really the pulses shouldn't change just because of, unless of course you're more stressed, but your pulse rate probably shouldn't change just because you're looking for work. So let's go back to age and see what that might look like. And here you can see the spread is about here. It's about a third to a fourth of this whole spread. And this spread, what it looks like. And so you can see the ratio of how much bigger this line is, how much smaller this line is to the length of this line. And that gives you an idea of what's happening. And so I would talk about this and get into this idea of what sampling variation is and look at the idea. So a different lesson might be, I've done the means, I've looked at the graphs, I've done the means on different days. And now I've come back to the same data set to look at what the variability is doing. And so this isn't where you just have this one that you do this one day and that's it. You only do it that one day of the semester. You can actually use these throughout the whole semester to kind of tie in the concepts all the way along and tie in the same data sets all the way along. So students are used to that same data set that they're working with and can see more different kind of concepts. And again, you can kind of keep looking around what's happening with these different samples. And you can see that there is definitely a spread between the average age or the mean age and what the variability is doing. So that might lead us into, once we know kind of that there's different variability, that might lead us into the concept of how do we know if there really is a true variability, if that model really is explaining that difference in variability. And so how do we actually do that would be the next question I would probably ask my students of where does that go and how does that involve? So then I probably would have them talk about, well, this spread is, again, how much variability is explained by the model. And this spread is how much variability is explained by just the data, the raw variables. And so you can see that this line, it's fairly long. And this one looks to be about, oh, I don't know, about a third of this line, maybe a fourth of this line. And so we can talk about how we could measure that and what that might look like, and how much is explained. So this is actually how much is explained by this. And that actually gets into the concept of an R squared. R squared is how much of the variability is explained by your model. So you can talk to your students and say, hey, look, this line is about, I don't know, about a third of this line. And this is R squared. So if you square a third, you get, I'm not good with the arithmetic, so I don't know exactly what you get, but you get something like this.
11%.
11%. Okay, perfect. Yeah, about that. Yeah. So this line here, the 1 minus R squared, is how much is unexplained. So you can see that there's not a great deal that's actually explained by this model. So in other words, it doesn't look like working status actually is explained by, or is involved in age, but you never know. But we don't see a lot of explanation here. 86%, 88%, sorry, is unexplained by the model. And let's take a different sample. So to keep track of this 11%, if we take a different sample, now suddenly it's at 4.8%. And only 95% is unexplained. And this one is about 5.9%. And notice that this line here is much smaller than this line. So you can kind of see that as you increase, as you take different samples, how this variability may change and how the R squared value might actually be changing. And then you wonder, well, how significant is it? Do we know if it's statistically significant or if it's not? So then we talk about our next lesson could be, all right, so now we have this idea of this R squared is explaining how much is of the how much the model.
What does the R squared turn out to be for pulse?
Oh yes, look at that. That's a good idea. So for pulse, the R squared is about 0.25%. Notice this is very small compared to that. Let's take another sample and see if it changes. So notice now it's about 0.55%. We'll keep taking it, keep track of that. Oh, hey, this one's 2.1%. So that kind of says to me that since all of my samples kind of have an R squared that's one, very, very small, and two, changes an awful lot, that this may not be, work may not be explaining your pulse rate at all. And so looking at this, notice it's jumping all over the place. We had a 0.5, now we're at 1.3. Now we're back down to 0.46 and so forth. And you're getting your R squared value is only about 99%, is about 99% is unexplained. And again, I would probably point out to my students that this is very, very short compared to this long bar here. And so that's kind of where I would go. So let's go back to one where we saw a little bit more happening. So we'll go back to age. And then we can see that we have a better R value, R squared value, and we'll keep looking at that. And then you could get into that concept of how do you know statistically it is significant? So one tab that we do have in this lesson is an F tab. So the F test, and it actually will show the students and show you how do we actually compute whether or not this is significant. And so I'm going to go over to the F test.
Okay, before you do that.
Yes.
So you were showing us before that big sample sizes, things tended to stay put.
Right.
And little sample size. So how much does the R squared depend on the sample? Does it just depend at all on the sample size or the p-value? Does that depend?
So let's look at that. So the R squared, when I have a sample size of 20, is about 1.2. If I take another sample, it's 16.7. So it is changing a great deal when we change our sample size. So it does seem to stabilize a little bit more when you have a larger sample. And again, that's because you have more of the data and you can do look at more what's happening. And notice it does jump around a lot more. So it's kind of like it's not a great indication. And again, you can see that this one looks like it's really good. 22% is explained and only 77% is not explained. Notice the line is much longer here than it is for this one. And we can keep looking at those different things. So now you would ask yourself, well, how do we know if it's significant? And so that's what the p-value represents. So let's talk about how did we get that p-value. So I will go to the Ftest and look at that. And when I click on this, it does give you the r-squared value it has right now, the 1 minus r-squared value, those are the same that we have over here. Again, this is explained is the r-squared, and the unexplained is this one, is the 1 minus r-squared. And this f is actually basically a ratio between the r-squared and the 1 minus r-squared. So the bigger the closer the bigger the r-squared is, the closer that ratio is to itself, you get a different f. Of course, it's not really that, because it also involves the degrees of freedom and of the residuals in the model. So we're going to look at how that plays a role, but that's kind of what it is. And then from the F statistic, you can calculate the p-value, which is what this does. So we have a fairly small sample. Let's look at what happens if I say the same size sample, but I take a new sample. So now my r-squared is 12%, my 1 minus r-squared is 88%, my ratio is a 1.16, and my p-value is only 0.34, so it's not great. Let's take another one. Notice when we have a smaller sample, your p-values kind of, this one looks like it's significant, doesn't it? Whereas the other ones were not. So it looks like it jumps around a lot. Again, we're no longer significant. So let's see what happens if we actually increase our sample size. Let's go back to our 500. Now we have a significant p-value. You again can see this ratio happening. Let's see what happens if we do a couple more. Notice your p-value is still pretty close to the same as we had before, even closer. And that's because I was saying it's not exactly just the ratio of the explained to the unexplained. It's also has the ratio of your degrees of freedom here. So the F statistic is actually kind of a combination of those two concepts. So as you can see, if you have degrees of freedom of your residuals and the degrees of freedom of your model, if you have a big enough sample, you're just going to have this number is going to be bigger anyway. And so you will, in fact, usually get statistical significance because of that. And so I would talk to my students about that, you know, the sample size gives us a lot more power, but also gives us things that may not be what we might think of as practically significant just because it is statistically significant. You can see that the p-value is pretty constant.
How would you measure the practical significance?
So what I look at, and I was going to get into that, but thank you for asking me. What I would look at for practical significance is 66.3% of the, and I'm going to go back to my graphic because I think it's more interesting. 6.37% of the variability is explained by the model. So even though the model is statistically significant, that 6.3% doesn't seem like it gives me much information. If I take another sample, it's still about 8.7%. It doesn't seem like it gives me a lot of explanatory variability either. It doesn't seem like it explains a lot. So it may be, yes, statistically we can see that there's a difference between these means, but is that really explained by age? And it doesn't look like it is.
Well, another way to look at it is that it looks like the not working people are more than 10 years older than the working people.
Right.
10 years is a pretty big difference in age.
Right. And that's because people are living longer and people are retiring earlier. Would be my guess. Would be a thought that you again could have your students think about. So looking at this, I don't see a lot of differences going on here. And so I would probably talk about the fact with my students that just because something's statistically significant doesn't mean that it's practically significant. It doesn't give you a lot of information. Let's go back and look at pulse and see what happens with that. So pulse, here we have a sample of 500 and we take another sample. This one's sort of significant, but this one you can tell is not the least bit. So statistically, these seem to be bouncing all over the place. This one's not. This one's not. You have some that aren't, but you have some that are. So it kind of says that because you have a bunch of samples that give you a different information going on about statistical significance, they don't seem to be really significant. And again, practically, let's get one that actually, so this one is statistically significant, but again, practically, it's only 1.82% of the variability in the model is explained by the model. So looking at this, not working people have a pulse rate about here, but there's not a lot of difference between the looking people. Just because somebody's not looking doesn't mean we can tell that their pulse rate's going to be higher or lower.
So if I'm following, we're used to calculating a p-value. We get one p-value for one set of data or for one exercise.
Mm-hmm.
But you're saying that the p-value also varies from sample to sample. I guess that's pretty obvious, but it seems to be varying by a lot.
Right.
That's kind of a surprise.
Yeah, it is. And this is something you can show your students about the fact that this is why statistics, we have to look at statistics more carefully and try to take samples over and over again and try to replicate the results. Because just because it worked for one sample doesn't mean it's going to be significant for another one. And this is what kind of shows us that the different samples don't always give you the same results. Whereas if we go back to age and work, they do seem to be giving us similar results. So this one would be a way to talk about in that concept of from the long time ago that you probably talked about at the beginning of the semester. You can bring that topic back up with the idea that, hey, we have to be able to replicate these. And just because you have it happen once doesn't mean it's going to happen for every sample.
So with the age and work, it looks like the p-value jumps around still, but the number of leading zeros seems to be pretty reliable there.
Right, and that's what I would look at is those number of leading zeros is pretty constant in all of these. You still have about 5 or 6 leading zeros in all of these.
But it varies a bit, which makes 0.05 kind of odd because if it can vary by a leading zero, 0.05 could be the same as 0.5.
Yeah.
Huh?
So I always wonder about the 0.5 and where we come up with that in the 0.05. So you can actually have that discussion of why is it 0.05 and where would you go with your students. And I wanted to show you one other one that I wanted to look at, and that was, I think it was BMI, I think it was. No, not BMI. Oh, I know what it was. It was still pulse rate. But we're going to look at, instead of work, we're going to look at depressed. And so here again, you can kind of see what's happening. But depressed, again, there's other choices you can do. You can look at the different ideas. You can do home ownership and whether or not they own or rent or some other thing they may be doing. You can also look at gender and what the pulse rate is for gender. Now with gender, there's only female, male. There's only 2 variables. So you can actually relate back to the idea that this is the same as a t-test. And so in fact, you can do an ANOVA instead of doing the t-test altogether with your students because you just have more variables with ANOVAs you can involve. So that's another thing I would probably show out to my students is that this ANOVA is very equivalent to a t-test if you only have 2 data values. Do you have any questions? All right, so I'm not hearing any questions.
So Kate,
yes.
I have a question, Kate. So in this webinar, you started out very simply, and then you got all the way through p-values and a subject that instructors don't usually cover, which is how much the p-value can jump around, whether the p-value is really a thing or whether it's just an indication. Would you do it all in one lesson like that?
No. I would have done this, like I said, I probably would have started off with a 1 lesson where I just give them the data and we look at the graph. So I probably would say, let's look at these different variables and see what happens what happens with depressed, and what does this data look like? So I'd probably look at the graphical. I probably would not have the show standard deviation on at first, just kind of show what's happening with the graphs. And what that graph tells me is this looks very spread out for being depressed, and what the age might be, and if you have several days of being depressed or you're mostly depressed, and kind of what that spread would look like and what the data would do. And then I would probably go ahead and show them the differences between sample size. So I probably would change and say, well, look at what happens with the sample size and what goes on. And then, which I find this, and then I probably show them multiple samples. So that would probably be one lesson. And then I'd probably do another lesson where I would look at the variability. So now we can see that there's a lot of, and I kind of talk about just with the data graphed here, there's a lot of variability in people that have had no depression and what their age is. And there's not as much variability if they've had several days. I also would point out to them that one of our data values is gone of the most because there was no values there. So remember, I would point out to them that this data value belongs with this line over here. And if there's no data, then there's no line. And I do another sample and do a few more samples and then say, oh, hey, most came back. So this data value does come back. And then I probably would do another lesson. And actually, I might even in this lesson, I might talk about the fact that, hey, look at this. We have one data value and that's why this is the mean. And then I probably would go and change the sample size and show what happens when I change it and what the variability might do. And I might change to a different response variable. I might look at what poverty would do and what would happen with poverty. Or I might look at whether or not somebody exercises, physically active. And I might look at that and see, well, what would the depression look like for that? And see if there's any kind of variability going on. And so I probably would kind of integrate that into my classes and kind of talk about it. Then I'd have another lesson if I'm now going into, let's go back to the one we were dealing with early, which is the age and, what was that? Age and work. And I would probably now talk about, well, why is there a difference between these? So I'd probably have a lesson that talked about there is a difference going on and what that difference might be. And then at that point, I might even incorporate what this R squared is about, or I might not. I might say that for another lesson, just talk about, hey, there seems to be a difference here. What's happening? What happens with different samples and whether or not there's still a difference. And then I get into this concept of the R squared and the 1 minus R squared, the explained and the unexplained. And that actually leads very nicely into regression discussion later. So you've already talked about R squared and explained and unexplained variability. So when you get into regression later, those concepts are already there. So this helps to introduce concepts early on. And then I would get into, okay, now that we see a difference, how do we know if it's statistically significant? So at that point, I'd probably have another lesson that talks about the p-values. And then I'd have another lesson that kind of talked about how the p-values could change and what they came from. And that's probably where I finally introduce the whole F statistic and the F-test calculation. So that's probably what I would do if I was teaching this topic. And teaching
so over several days or spread apart by weeks or something like that.
I might even do it for the whole semester, introduce this data set early on, and then a few weeks later, introduce the next topic with the same data set and just keep moving along all the way through the semester. So I'm introducing that same data set all the way along.
I have a question for you about statistics. It looks like all you really need to do statistics is that button at the bottom that says get a new sample. And then all you have to do is look at lots and lots of samples and see how steady the results are. If they're steady, you've got something, and if they're not steady, you don't. Why not just do that?
Well, what is that normally we can't just take lots and lots and lots of samples. We can in this case because we have the data already available to us that somebody else collected, but if you're doing your own sample, you can't do this. You probably don't have the time and money to do where you take a bunch of samples. So that's what
Kate, I have a question. If you're doing this over, which it's great, I love it, over the course of a semester, do you do anything that the students have to do outside of class in terms of like assessments, homework, or anything? Like, what kind of questions would you have them do, or like what would you do for that?
So again, would depend on when I'm teaching this, but if I was early on, I would probably say to them, here's our data set that we're working with. I was working with age versus work, but are there other variables in here that you may be more interested in? And I'd have them early on look at a different set of grouping. They might be interested in their age and whether or not, especially if they're college students, you might look at, have they ever had sex? So that might be something they might want to look at, and kind of have them look at different variables and then analyze what story. I like to talk in my classes always about what story does the graph tell you? And can they look at these graphs and tell a story about this information? So I might have them pick one of these many explanatory variables and then pick one of the response variables and see if they can tell a story about it. So I probably would have them do that early on, and then I'd probably have them talk about what's the variability of these groups a little bit later on when I've introduced the idea of variability. Which one of your grouping that you picked has more variability? And so those be kind of the out of class activities they could do, is kind of looking at their own response variables and explanatory variables. What do they think is happening?
And is there, I know Danny had mentioned there's going to be like an extra tab where we can see what the data is, but maybe is there going to be like a quick sheet of like what all these variables mean? For instance, like when you go to poverty, what do those numbers mean on the side, the 1 through 5?
Yes, that's the code book. And this is like the first generation one. You can move on from that era. And that was one of the things that people pointed out, is that we really need to have the code book right there. So
okay, cool.
There. To go back to your first question, though, here's another kind of exercise you could give students. You could say, find me a pair of variables here where for a sample size of 100, you really do see a significant variable. Or find me one where for a sample size of 1,000, you still can't see a significant relationship.
I like that question, because then it could be something from the beginning where they're just visually seeing a difference, and then later they can say it using p-values, so I like that because it's a little more open-ended.
Right.
Another one, Kate, if you turn on the standard deviations. Okay, so imagine that instead of the whole app here, you just cut out that graphic and you gave them a homework sheet with that graphic. You could ask them, what's the standard deviation of the raw values? And they'd have to measure the length of that gray bar. You could ask them, what's the value of R squared? And they'd have to see, well, the smaller one is about half the larger one, so R squared is going to be 1/2 squared. Right? So those are little calculation type exercises that they can do visually without having to get into lots and lots of detail, but it does exercise those concepts.
This leads me to my next question. Can we take snippets of this or screenshots and use this for worksheets? Is there copyright issues that we would have to think about? Like,
no, this is a StatPREP product. So it's free for anyone to use. It's open source. We do have to deal with the question of whether some students should be able to access the source, which I think not, maybe. But for teachers, anything goes. And in fact, the apps are written so that if you just want to have the graph without any interactivity, you can do that too.
Okay.
Cool. Thank you.
I had a few questions. So I do love the app. I think it's really cool. And are there a way to do additions to it for like maybe seeing like the standard deviations or even like confidence intervals of each group? So
Well,
they can look at variability, you know, between groups to that variability within, or just comparing even like confidence intervals between the groups. And
yeah, I guess I have two different answers to that question. One is yes, we can put anything in here that you want to put in here. And this is, you know, the StatPREP's team first guess about what might be useful, but you have your own insights. And so feedback from the users is really important. The other answer is no, that we wanted to keep each app pretty streamlined. So there's another app, the T-Test app, which doesn't have this F stuff in it, but which does let you show the confidence intervals on the mean and show how those vary with size. And
Okay.
then another app about regression, which lets you see, you know, both slopes and confidence bands, but doesn't give you, you know, means, only works for two quantitative variables. So there's that trade-off. You'll have to tell us what works, whether it's better to have several apps that do kind of a simple display, or one app that does everything that anyone might want to do. I guess my bias is towards the first of those.
But there is a blog on the StatPREP site. If you could put your questions and comments in that blog, we are looking over the comments, and we'll see if we can't incorporate what you have to say. If we see a lot of people say they want something, then we would know to incorporate that.
Do you want to bring up that blog?
Sure. So
And-
on the StatPREP website, the blog is, actually, I don't know where it is.
Go down, I think it's in March.
March.
Little apps for teaching stats.
And here at the bottom of that
Yeah,
little
okay.
application stats is a place to leave comments. So all I did was go into, from the main site, I went down to the little app for teaching stats. I went into those. And then at the bottom of that, you'll see a place to where you can make comments, and anybody can see what you're having to say. Okay.
okay.
And the links to the apps on the server are there in the blog. You can see it now on the screen.
So they're right here.
Yeah, and
And the instructor orientations are right next to them. So this one belongs with wise density instead of counts. This one involves with the sampling and confidence app.
And yeah, those instructor orientations are meant to give you ideas for how you might use the apps in teaching. They're not meant to be, you know, lab 7 in your course, but they might give you an idea for how you want to structure that. And they try to explain what the different components of the apps are.
Okay. That's awesome.
So are there any other questions?
Usually in these webinars, we've been having a kind of workshop segment after the webinar where people were using computer commands and such to do things related to the subject. But with these apps, it's really clicking buttons. And I think the best way to find out what they're about is just to use them, to play with them.
All right, so if there's no more questions, we certainly will answer any questions through email. You can email any of the people on the StatPREP site, and we will answer it or post in the blog, and we will certainly answer your questions. All right.
Okay. Well, Kate, thank you for leading us through that ANOVA app. And thanks to all of you. And we do look forward to hearing how you use these and how we can help you use them better.
Thank you so much.
Yeah.
That was really great.
Yes. Thank you.
Thank you.
Thanks, everyone.